Imagine standing beneath a sky where the planet above you isn't just a distant speck of light, but a colossal sphere with rings so vast they stretch farther than your imagination can grasp. Saturn, the jewel of our solar system, has puzzled scientists and dreamers alike for centuries. From its shimmering rings to its bizarre moons that behave more like characters in a cosmic mystery novel, this planet is a treasure trove of unanswered questions. Today, we embark on an incredible journey through 25 unexplained mysteries of Saturn. Each one is a puzzle piece waiting to be discovered, revealing secrets about the origins of our universe and perhaps even life itself. Picture this: a moon spewing water into space, another with lakes made not of water but methane, and a hexagon-shaped storm at the planet's north pole that defies everything we thought we knew about weather patterns. These are just some of the wonders we will explore together, so buckle up because what lies ahead might change how you see the cosmos forever. Let's begin with one of Saturn's most iconic and perplexing features, the hexagon at its north pole. This six-sided jet stream, first spotted by the Voyager missions in the early 1980s and later studied in greater detail by Cassini, is unlike anything else we've observed in the solar system. Imagine a storm so massive that it could swallow Earth whole, yet maintaining an almost perfect geometric shape for decades. That's exactly what this hexagonal structure represents. What makes the hexagon even more intriguing is its stability. Unlike storms on other planets, which tend to dissipate or change form over time, this feature has remained remarkably consistent since its discovery. Scientists are still trying to figure out how such a complex atmospheric phenomenon can persist for so long without altering its shape. Theories abound, but none fully explain why the winds move in this precise pattern rather than spiraling outward or breaking apart entirely. Another layer of mystery comes from the hexagon's changing colors. Over the years, images captured by Cassini revealed shifts in hues, from a soft blue to deep gold and even reddish tones. These transformations occur seasonally, suggesting a connection between sunlight and the chemical composition of Saturn's atmosphere. However, the exact mechanisms driving these changes remain unclear. Is it due to photochemical reactions triggered by solar radiation? Or could there be something deeper happening within Saturn's atmosphere that we haven't uncovered yet? To truly appreciate the hexagon's uniqueness, let's take a closer look at what space probes have shown us. High-resolution images and animations reveal swirling clouds moving along the edges of the hexagon at incredible speeds, while a central vortex sits quietly inside. It's as if nature itself decided to draw a polygon in the clouds, defying all conventional wisdom about fluid dynamics. For viewers who may not grasp the scale, think of it this way. Each side of the hexagon spans roughly 20,000 kilometers, about twice the diameter of Earth. While simulations attempt to replicate the conditions necessary for forming such a structure, no laboratory experiment has successfully produced a perfect hexagon under similar atmospheric circumstances. This discrepancy highlights just how much we still don't understand about Saturn's unique environment. Some researchers propose that standing waves generated deep within the planet's atmosphere might influence the shape of the jet stream, but proving this hypothesis remains elusive. As we delve deeper into the mysteries surrounding Saturn, the hexagon serves as a powerful reminder of how much there is left to discover. Its existence challenges our understanding of planetary atmospheres and opens doors to new possibilities about weather systems across the universe. And though we've made significant strides in studying this enigma, many questions linger unanswered, inviting future generations of scientists to continue unraveling its secrets. With the hexagon now firmly etched in our minds, let's turn our attention to another fascinating aspect of Saturn, a marvel that lies not in its atmosphere but in the vast expanse of its rings. Shifting our gaze outward from Saturn's mesmerizing hexagon, we encounter another breathtaking feature that has captivated scientists and stargazers alike for centuries: its dazzling ring system. These rings are not just a visual spectacle, they represent one of the most intricate puzzles in planetary science. Stretching hundreds of thousands of kilometers across yet only tens of meters thick, the rings orbit Saturn like a celestial masterpiece, inviting us to explore their origins, composition, and enduring mysteries. Scientists have proposed several theories about how these rings came into existence. One prevailing idea suggests that the rings formed when a moon or comet ventured too close to Saturn and was torn apart by its immense gravitational pull. Another hypothesis posits that the rings could be remnants of material left over from the planet's formation billions of years ago, never coalescing into solid bodies. Regardless of their origin, what is certain is that the rings consist primarily of water ice particles, ranging in size from microscopic dust grains to boulders as large as houses. This icy makeup gives the rings their characteristic brilliance, reflecting sunlight with almost mirror-like precision. Despite their apparent permanence, the rings are far from static. In fact, they are constantly evolving due to interactions between the particles within them and external forces such as Saturn's moons. For instance, shepherd moons like Pan and Daphne's help maintain the structure of certain parts of the rings by influencing the movement of nearby particles through gravitational tugs. These dynamic processes create features like gaps, waves, and even spiral patterns, offering researchers valuable clues about the mechanics at play. One of the most puzzling aspects of Saturn's rings is their striking brightness. Unlike many other celestial objects, which darken over time due to exposure to cosmic radiation and micrometeorite impacts, Saturn's rings remain remarkably pristine. Why haven't they accumulated more debris or developed a darker hue? Some experts believe this could be due to ongoing replenishment mechanisms, where fresh material continuously replaces older, dirtier particles. Others suggest that the rings might simply be younger than previously thought, having formed relatively recently in geological terms, perhaps just 100 million years ago. Another critical question concerns the longevity of the rings themselves. Recent studies indicate that the rings may not last forever. Evidence suggests that some of the material is gradually spiraling inward toward Saturn due to gravitational drag, meaning the rings could eventually fade away entirely. While this process is likely to take tens of millions of years, it raises intriguing possibilities about how long these iconic structures will grace our skies and what Saturn might look like without them. To truly appreciate the complexity of Saturn's rings, consider the wealth of data collected by missions like Cassini. High-resolution images reveal an astonishing level of detail, showing individual ringlets, spokes, and shadowy bands cast by the planet itself. These visuals provide a window into the intricate dance of particles and forces that define the ring's behavior. As technology advances, future missions may unlock even more secrets hidden within this stunning phenomenon. In summary, Saturn's rings stand as both a symbol of beauty and a testament to the mysteries still waiting to be unraveled. From their possible origins to their uncertain futures, every aspect of the rings challenges our understanding of planetary dynamics. As we continue exploring this enigmatic system, one thing remains clear. Saturn's rings remind us that there is always more to learn about the wonders of our universe. With this in mind, let's now journey deeper into the realm of Saturn's moons, beginning with Enceladus, a tiny world harboring big surprises beneath its frozen surface. Venturing further into the wonders of Saturn's moons, we arrive at Enceladus, a small yet extraordinary world that has become one of the most intriguing targets in our search for extraterrestrial life. While it may appear as just another icy satellite from afar, closer inspection reveals a dynamic and potentially habitable environment hidden beneath its frozen crust. In 2005, NASA Cassini spacecraft made an astonishing discovery. towering plumes of water vapor and ice particles jetting hundreds of kilometers above Enceladus' surface. These geysers erupt from fissures near the Moon's south pole, known colloquially as tiger stripes, which are long, warm fractures on the otherwise frigid landscape. The sheer force behind these eruptions suggests powerful processes occurring deep within the Moon. Scientists believe that tidal heating caused by Saturn's gravitational pull generates enough energy to drive liquid water upward through cracks in the ice, creating the spectacular plumes we observe today. But the jets themselves are only part of the story. Analysis of the material ejected by Enceladus shows a rich composition of water, salts, ammonia, and organic molecules, ingredients essential for life as we know it. This evidence strongly supports the existence of a vast subsurface ocean lurking beneath the Moon's icy shell. Recent studies indicate that this ocean is not merely localized but spans the entire globe, making Enceladus one of the few places in the solar system where such conditions exist. The implications of this finding are profound. A global ocean means that heat and chemical reactions could circulate throughout the interior, providing stable environments where life might thrive. Moreover, the presence of hydrothermal activity at the seafloor, a process similar to what occurs on Earth, is thought to be driving the production of complex organic compounds detected in the plumes. Such activity creates ecosystems independent of sunlight, offering tantalizing hints about the potential for life even in the darkest corners of the cosmos. What makes Enceladus particularly exciting is how accessible its secrets seem to be. Unlike Europa or Ganymede, whose oceans are buried under thick layers of ice, Enceladus generously sends samples of its subsurface waters directly into space. Future missions could collect and analyze these particles without needing to drill through miles of ice, significantly advancing our understanding of this alien realm. As we ponder the possibilities raised by Enceladus, let's also consider the broader implications. If life does exist here, or did exist in the past, it would redefine our understanding of biology and expand the boundaries of where we should look for signs of life elsewhere in the universe. With each new observation, Enceladus continues to reveal itself as a treasure trove of scientific marvels, proving once again that the smallest worlds can hold the biggest mysteries. Let's now shift our attention to Titan, where an entirely different set of puzzles awaits exploration. Moving from the icy wonders of Enceladus, we journey now to Titan, Saturn's largest moon and a world unlike any other in our solar system. Imagine a place where the air is thick with nitrogen and liquid methane flows like water on Earth. This bizarre yet fascinating environment makes Titan one of the most intriguing destinations in space exploration. Titan's atmosphere stands out as one of the densest in the solar system, composed primarily of nitrogen with traces of methane and other hydrocarbons. It blankets the Moon in an orange haze so thick that it obscures its surface from view when observed from afar. Interestingly, this atmospheric composition creates a cycle reminiscent of Earth's water cycle, but instead of water, methane plays the starring role. Methane evaporates from lakes and seas, forms clouds, rains down onto the surface, and eventually flows back into these bodies through rivers and streams. The presence of liquid hydrocarbons on Titan's surface adds another layer of mystery. Unlike water, which freezes at temperatures below 0 degrees Celsius, methane remains liquid at the frigid temperatures found on Titan, around -180 degrees Celsius. Scientists have identified vast reservoirs of liquid methane and ethane in the form of lakes and seas concentrated near the poles. These features are so prominent that they resemble terrestrial counterparts, albeit filled with substances foreign to our planet. One particularly striking aspect of Titan is its surface geography, revealed thanks to radar imaging by spacecraft like NASA Cassini mission. The images show sprawling plains, towering dunes made of solidified hydrocarbon particles, and even impact craters softened by weathering over time. But perhaps the most captivating sights are the dark, mirror-like patches representing the lakes and seas scattered across the landscape. Kraken Mare, Ligeia Mare, and Punga Mare are some of the largest known examples, each comparable in size to the Great Lakes of North America. Despite their alien nature, these hydrocarbon-rich environments raise questions about the potential for life or probiotic chemistry. While liquid methane does not support life as we know it, the complex organic molecules detected in Titan's atmosphere hint at processes that could mimic early stages of biological development. Some researchers speculate that exotic forms of life might exist within these methane seas, thriving under conditions vastly different from those on Earth. As we marvel at Titan's unique characteristics, one cannot help but wonder what secrets lie beneath its smoggy veil. Future missions aim to unlock these mysteries, whether by sending probes to study its atmosphere or deploying submersibles to explore its enigmatic lakes. For now, Titan remains a tantalizing puzzle, challenging our understanding of planetary science and broadening our perspective on the possibilities of life beyond Earth. With such profound implications, Titan continues to captivate scientists and dreamers alike, promising answers and more questions as we delve deeper into its strange and wondrous world. Shifting our focus from the enigmatic moon Titan, let us now explore another captivating mystery of Saturn, the transient radial markings known as spokes that occasionally grace its magnificent rings. These peculiar features were first observed by the Voyager spacecraft in the early 1980s and have since intrigued scientists worldwide. Unlike the stable structure of the rings themselves, these spokes appear suddenly, float across the ring system, and then vanish just as mysteriously. The spokes typically form in Saturn's B ring, which is the densest and brightest part of the ring system. They manifest as dark or bright markings that stretch radially outward, resembling the spokes of a wheel. Interestingly, their orientation changes as they move along the rings, always pointing toward the planet's rotational axis. This unique behavior suggests a connection to Saturn's magnetic field, though the exact mechanism remains elusive. What scientists do know is that these phenomena are closely tied to specific conditions within the rings. Spokes tend to occur when the rings are at certain angles relative to the Sun, suggesting that sunlight plays a role in their formation. Additionally, observations indicate that the particles composing the spokes are exceptionally small, likely only a few micrometers in size. These tiny grains may become electrically charged due to interactions with Saturn's magnetosphere, causing them to levitate above the main ring plane. Despite these insights, many questions remain unanswered. For instance, why do spokes only appear during specific times of Saturn's year? Observations reveal that they are most common around the planet's equinoxes but disappear entirely during other seasons. Researchers hypothesize that this seasonal variation could be linked to temperature fluctuations within the rings, affecting the charging properties of the particles involved. Moreover, the process governing the disappearance of spokes is equally puzzling. Once formed, they seem to dissipate gradually, fading into the surrounding ring material. Some theories propose that collisions between spoke particles and larger ring debris might neutralize their charge, causing them to settle back into the main ring plane. However, direct evidence supporting this hypothesis has yet to emerge. Images captured by NASA Cassini mission provide some of the best glimpses of these ephemeral structures. The spacecraft documented numerous instances of spokes over its 13-year tenure in orbit around Saturn, offering valuable data for analysis. One particularly striking observation revealed how the spokes' appearance varied depending on whether they were viewed from the sunlit or shadowed side of the rings. Such findings highlight the complexity of these phenomena and underscore the need for further investigation. In summary, the disappearing spokes in Saturn's rings represent one of the most intriguing puzzles in planetary science. While progress has been made in understanding their characteristics and behavior, much about their origins and life cycle remains shrouded in mystery. As we continue to study these fascinating features, they remind us of the vast wonders still waiting to be uncovered in our solar system. Moving deeper into the enigmatic heart of Saturn, let us now uncover the mysteries surrounding its internal structure. Despite decades of observation and sophisticated modeling, our understanding of what lies beneath Saturn's swirling clouds remains incomplete. The planet's immense size and gaseous composition make direct exploration nearly impossible, leaving scientists to rely on indirect methods and theoretical models to piece together its hidden anatomy. At the core of Saturn lies one of the most perplexing puzzles in planetary science. Current evidence suggests that Saturn possesses a solid core made primarily of rocky and metallic materials, surrounded by layers of liquid metallic hydrogen, molecular hydrogen, and helium. However, the exact nature of this core, its size, composition, and density remains uncertain. Estimates vary widely, with some models proposing a relatively small, dense core no larger than Earth, while others suggest a much more massive structure extending thousands of kilometers into the planet's interior. One major challenge in determining Saturn's internal makeup stems from its extreme conditions. The pressures and temperatures at the planet's center are staggering, far exceeding anything we can replicate in laboratories here on Earth. These intense forces alter the behavior of materials in ways that are not yet fully understood, complicating efforts to predict how elements interact under such circumstances. For instance, hydrogen, the most abundant element in Saturn's atmosphere, behaves strangely under high pressure, transitioning from a gas to a liquid metal capable of conducting electricity. This transformation plays a crucial role in shaping Saturn's magnetic field and influencing the distribution of mass within the planet. Another hurdle arises from the difficulty of measuring Saturn's gravitational field with precision. By studying variations in gravity, researchers hope to infer details about the planet's internal density distribution. However, these measurements must account for numerous factors, including the effects of Saturn's rapid rotation, which causes it to flatten slightly at the poles and bulge at the equator. Additionally, the presence of the rings introduces further complications, as their gravitational influence can obscure subtle signals emanating from the planet itself. To address these challenges, scientists have developed several competing models of Saturn's interior. One prominent theory posits that the core is surrounded by a layer of rainout, where heavier elements gradually settle through the outer layers of hydrogen and helium over time. Another model suggests that Saturn's core may be less distinct than previously thought, blending seamlessly into the surrounding layers rather than forming a sharp boundary. Each hypothesis offers a different perspective on how Saturn evolved and continues to function today. Advances in technology and data collection have begun to shed light on these uncertainties. Observations from NASA Cassini mission provided valuable insights into Saturn's gravitational field and internal dynamics, refining existing models and sparking new questions. Future missions equipped with even more advanced instruments may one day reveal the true nature of Saturn's mysterious core, helping us unlock the secrets of this gas giant's origins and evolution. In summary, Saturn's internal structure represents another frontier of discovery in our quest to understand this remarkable planet. While significant progress has been made, many aspects of its inner workings remain shrouded in mystery. As research continues, each new finding brings us closer to unraveling the complexities of Saturn's hidden depths, inspiring awe and curiosity about the wonders of our solar system. Shifting our gaze from Saturn's enigmatic interior to one of its most peculiar moons, let us explore the fascinating case of Hyperion and its chaotic rotation. Among Saturn's extensive family of satellites, Hyperion stands out not only for its irregular shape, but also for its utterly unpredictable behavior as it tumbles through space. Hyperion is a small moon with a porous, spongy appearance that resembles a giant cosmic sponge drifting in orbit around Saturn. Its surface is pockmarked with craters, some so deep they appear almost cavernous, giving the moon an otherworldly texture. This unique appearance stems from its low density, which suggests that Hyperion may be composed mostly of water ice mixed with smaller amounts of rock. Such a composition makes it incredibly fragile compared to many of Saturn's other moons. What truly sets Hyperion apart, however, is its chaotic rotation. Unlike most celestial bodies which spin steadily on their axes, Hyperion exhibits a wild and erratic motion that defies easy prediction. Imagine trying to track the orientation of a spinning top if it were constantly being jostled by invisible forces. This gives you an idea of how difficult it is to anticipate where Hyperion's face will point at any given moment. Scientists attribute this unusual behavior to the moon's irregular shape and gravitational interactions with larger moons like Titan and Iapetus. The mathematics behind Hyperion's tumbling motion reveals just how complex these dynamics can become. In essence, its rotation is governed by what scientists call a three-axis rotation, meaning it spins along all three axes simultaneously rather than maintaining a single axis of rotation like Earth or the Moon. This results in a motion so unstable that even tiny disturbances such as gravitational nudges from nearby objects can cause significant changes in its orientation over time. As a result, predicting exactly where Hyperion will be pointing after even a short period becomes nearly impossible. This unpredictability has fascinated astronomers for decades. It serves as a real-world example of chaotic systems, where small variations in initial conditions lead to vastly different outcomes, a hallmark of chaos theory. By studying Hyperion's motion, researchers gain insights into broader principles governing celestial mechanics and the long-term stability of orbits throughout the solar system. In addition to its intriguing rotational dynamics, Hyperion's surface offers plenty of opportunities for exploration and wonder. Up-close images captured by NASA Cassini spacecraft reveal a landscape unlike anything else in the solar system. The Moon's cratered exterior bears witness to countless impacts over billions of years, yet its porous structure seems to cushion these blows, preserving much of its original form. Some craters are so large they stretch across significant portions of the Moon's surface, creating dramatic shadows that highlight its rugged terrain. As we continue to study Hyperion and its chaotic dance around Saturn, each new discovery adds another layer to our understanding of this remarkable moon. Its unpredictable nature reminds us of the complexity and beauty inherent in the universe, challenging us to rethink assumptions about how celestial bodies behave. And while Hyperion may never settle into a predictable rhythm, its very existence invites us to marvel at the wonders hidden within Saturn's vast and mysterious realm. Moving from the chaotic dance of Hyperion, let us now turn our attention to another one of Saturn's moons that harbors its own set of mysteries, namely Iapetus and its extraordinary equatorial ridge. This moon is a true enigma in its own right, with features that continue to puzzle scientists even after decades of study. Iapetus stands out among Saturn's moons for several reasons, but perhaps none as striking as the massive mountain range that runs almost perfectly along its equator. Stretching over 1,300 miles in length, this ridge can reach heights of more than 12 miles, making it one of the tallest known structures in the solar system. What makes this feature all the more remarkable is its alignment. It hugs the moon's equator so precisely that it seems almost artificial. Yet, there is no doubt that it is a natural formation, though how and why it formed remains hotly debated. There are several competing theories about the origin of Iapetus' equatorial ridge. One hypothesis suggests that the ridge could have formed during a period when Iapetus was spinning much faster than it does today. In this scenario, the rapid rotation would have caused the moon to bulge at its equator, creating a structure similar to what we see now. Over time, as the moon slowed down due to tidal forces from Saturn, the bulge solidified into the ridge we observe today. While this explanation accounts for the ridge's location, it struggles to explain its height and the fact that not all rapidly rotating bodies exhibit such dramatic equatorial features. Another theory posits that the ridge might be the remnants of a former ring system around Iapetus. According to this idea, material from a long-lost ring could have gradually accumulated along the Moon's equator, forming the ridge over millions or billions of years. Proponents of this theory point to evidence of similar processes occurring elsewhere in the solar system, such as the rings surrounding Saturn itself. However, critics argue that the amount of material required to build such a towering structure would need to be immense, and current observations do not provide clear support for the existence of a past ring system. A third possibility involves impacts from large celestial objects. Some researchers propose that a massive collision or series of collisions could have deposited debris along Iapetus' equator, eventually coalescing into the ridge. While intriguing, this theory faces challenges explaining why the ridge follows the equator so closely and maintains such a consistent width throughout most of its length. Despite these hypotheses, none fully account for every aspect of the ridge's formation, leaving scientists to consider combinations of factors or entirely new explanations. The complexity of the problem lies in reconciling the ridge's size, shape, and position with the physical properties and history of Iapetus itself. Detailed imagery captured by NASA's Cassini mission provides tantalizing glimpses of the ridge's intricate structure. These images reveal jagged peaks, steep cliffs, and shadowy valleys that stretch endlessly across the Moon's surface. The sheer scale of the ridge becomes apparent when viewed up close, offering clues about its composition and potential origins. For instance, the ridge appears to consist largely of water ice mixed with some darker materials, suggesting a connection to Iapetus' overall makeup. What adds to the intrigue is the fact that nothing quite like Iapetus Ridge exists anywhere else in the solar system. Its uniqueness raises profound questions about the conditions under which it formed and whether similar processes could occur on other worlds. As research continues, each new observation brings us closer to unraveling the secrets of this mysterious feature, while deepening our appreciation for the diversity of celestial phenomena. With the mystery of Iapetus' equatorial ridge still unsolved, our exploration of Saturn's wonders takes yet another fascinating turn, reminding us just how much there is left to discover in the depths of space. Venturing deeper into the enigmatic realm of Saturn, we now delve into another peculiar phenomenon, its mysterious radio emissions. These strange signals emanating from the planet have puzzled scientists for decades, revealing yet another layer of complexity in our understanding of this distant world. Unlike anything else in the solar system, Saturn's radio emissions exhibit an unusual characteristic. They vary significantly between its northern and southern hemispheres. This asymmetry has sparked numerous questions about the nature of these signals, their origins, and what they might mean. To begin with, let us explore the basics of these emissions. Saturn broadcasts low-frequency radio waves known as Saturn kilometric radiation, or SKR for short. Despite the name, these are not visible to human eyes but can be detected using specialized instruments aboard spacecraft like NASA Cassini probe. The sounds produced by these radio waves resemble crackling static when converted into audio format, creating an eerie symphony that echoes through space. While some may find it unsettling, these noises hold valuable clues about the inner workings of Saturn's magnetic field and atmosphere. The variation in frequency and intensity between Saturn's hemispheres is particularly intriguing. Data collected during the Cassini mission revealed that the northern hemisphere emits higher frequency signals compared to the south. At first glance, this difference might seem minor, but it points to fundamental disparities in the way each hemisphere interacts with Saturn's magnetosphere, the region dominated by its magnetic field. Researchers believe that factors such as seasonal changes, plasma dynamics, or even localized disturbances within the magnetosphere could play a role in shaping these differences. Efforts to decode these radio emissions have led scientists down several paths of inquiry. One prevailing theory suggests that the signals originate from powerful lightning storms deep within Saturn's thick atmosphere. Lightning generates radio waves as part of its discharge process, and given Saturn's massive size and storm activity, it seems plausible that these events contribute significantly to the observed emissions. However, while lightning explains some aspects of the phenomenon, it does not fully account for the distinct hemispheric variations. Another line of investigation focuses on Saturn's magnetic field itself. Unlike Earth, which has a relatively stable dipole field, Saturn's magnetic environment exhibits complex behavior. Its axis of rotation aligns almost perfectly with its magnetic poles, leaving researchers scratching their heads over how such alignment influences the generation of radio waves. Some speculate that subtle shifts in the magnetic field caused by external forces, such as interactions with the solar wind, could modulate the emission patterns differently across hemispheres. In addition to these hypotheses, there remains the tantalizing possibility that Saturn's radio emissions encode information about processes occurring deep beneath its cloud tops. For instance, studying the timing and structure of these signals could shed light on the true length of Saturn's day, a question that continues to elude definitive answers due to the planet's gaseous composition masking traditional markers of rotation. While much progress has been made in interpreting Saturn's radio emissions, many mysteries remain unsolved. Each new observation brings fresh insights but also raises additional questions, fueling ongoing research into this fascinating domain. To give you a sense of these otherworldly sounds, here is a sample recording captured by the Cassini spacecraft, allowing you to experience firsthand the haunting beauty of Saturn's voice. As we listen together, remember that every crackle and pop carries secrets waiting to be uncovered in the depths of space. With this auditory glimpse into Saturn's hidden world, we continue our journey into the unknown, where each discovery opens doors to new possibilities and deepens our connection to the cosmos. Shifting our gaze from Saturn's mysterious radio emissions, we now turn to one of the planet's most spectacular and recurring phenomena, the Great White Spot. This colossal storm system erupts roughly every 3 decades, painting Saturn's atmosphere with an immense, swirling patch of white clouds that can stretch thousands of kilometers across. The Great White Spot is not just a meteorological marvel, but also a profound mystery that continues to challenge scientists' understanding of planetary weather patterns. The first recorded observation of the Great White Spot dates back to 1876, when astronomers noticed an unusually bright feature on Saturn's surface. Since then, similar storms have been documented in 1903, 1933, 1960, 1990, and most recently in 2010. Each outbreak shares striking similarities, yet each event also brings unique characteristics that deepen the intrigue surrounding these periodic tempests. What makes the Great White Spot particularly fascinating is its timing. It tends to occur near Saturn's northern hemisphere summer solstice, though the exact triggers remain elusive. To understand what causes these massive storms, researchers have turned to data collected during the Cassini mission, which captured detailed images of the 2010 eruption. The storm began as a small disturbance in Saturn's atmosphere, but quickly grew into a monstrous system that wrapped entirely around the planet, spanning more than 3 Earth diameters at its peak. Observations revealed that the storm drew energy from deep within Saturn's interior, dredging up water vapor and ammonia ice from layers far beneath the visible cloud tops. This process created towering thunderheads and violent lightning strikes, some of which were hundreds of times stronger than those on Earth. Despite advances in technology, many questions about the Great White Spot remain unanswered. For instance, why does this phenomenon occur approximately every 30 years? Scientists suspect that the timing may be linked to Saturn's seasonal cycles, as the planet takes nearly 30 Earth years to orbit the Sun. However, the precise mechanisms driving the formation and intensity of these storms are still under investigation. Some theories propose that internal heat buildup combined with atmospheric instability creates conditions ripe for such explosive events, while others suggest that external influences like solar radiation play a role in initiating the storms. Another intriguing aspect of the Great White Spot is its behavior after reaching maximum extent. Unlike terrestrial hurricanes, which weaken when they move over land or cooler waters, Saturn's storms eventually dissipate due to interactions between their high-altitude winds and lower-level jet streams. These dynamics help shape the storm's evolution, causing it to break apart into smaller vortices before finally fading away. Studying this process provides valuable insights into how energy moves through Saturn's atmosphere and how different layers interact during extreme weather events. Visual records of the Great White Spot offer breathtaking glimpses into the power and beauty of these storms. Images captured by ground-based telescopes and spacecraft reveal intricate details of the storm's structure, including swirling arms, chaotic turbulence, and vibrant colors that highlight variations in temperature and composition. These visuals serve not only as stunning reminders of nature's grandeur, but also as critical tools for advancing scientific knowledge. As we continue exploring Saturn's mysteries, the Great White Spot stands as a testament to the planet's dynamic and ever-changing environment. Each new observation adds another piece to the puzzle, bringing us closer to unraveling the secrets behind these awe-inspiring storms. Yet, much work remains to fully comprehend the forces shaping Saturn's atmosphere and perhaps uncover clues about weather systems elsewhere in the universe. Moving our focus now to one of Saturn's most enigmatic moons, Phoebe, we encounter a celestial body whose peculiar composition and origin raise more questions than answers. Phoebe stands out among Saturn's moons due to its distinctive appearance and behavior, making it a subject of intense scientific curiosity. Unlike many of Saturn's icy satellites, Phoebe has a dark, heavily cratered surface that suggests an intriguingly different past. Phoebe's composition is particularly unusual, as studies reveal that it contains a mix of water ice, carbon dioxide, and complex organic compounds. This combination is not commonly found in objects native to the Saturnian system, leading scientists to speculate that Phoebe may have originated elsewhere in the solar system. Evidence from the Cassini mission indicates that Phoebe's surface closely resembles that of Kuiper belt objects, which are remnants from the early days of the solar system located beyond Neptune. This resemblance suggests that Phoebe might have been captured by Saturn's gravitational pull billions of years ago, rather than forming alongside the planet. The moon's irregular orbit further supports this hypothesis. Phoebe travels in a retrograde path, meaning it moves in the opposite direction to Saturn's rotation. Such orbits are rare for objects that form within a planet's vicinity and are typically associated with captured bodies. The combination of its chemical makeup and orbital characteristics makes Phoebe a fascinating case study for understanding how objects can migrate across vast distances in the solar system. Detailed observations of Phoebe's surface reveal a landscape scarred by countless craters, some of which are so large they nearly span half the moon's diameter. These craters provide valuable clues about Phoebe's history, including the frequency and intensity of impacts it has endured over billions of years. One particularly striking feature is the enormous crater named Osier, which stretches approximately 75 kilometers across. Images captured by the Cassini spacecraft show the intricate details of these craters, revealing layers of material ejected during impact events. These layers help scientists piece together the internal structure of Phoebe and determine whether it harbors any hidden reservoirs of water or other substances beneath its rugged exterior. Another aspect of Phoebe's mystery lies in its potential connection to the formation of Saturn's rings. Researchers believe that debris kicked up from collisions on Phoebe could contribute to the fine particles found in Saturn's outermost rings. This theory adds another layer of complexity to the relationship between Saturn and its moons, highlighting the interconnectedness of processes occurring throughout the system. Studying Phoebe offers insights into broader questions about the origins of small bodies in the solar system and their roles in shaping planetary environments. By analyzing its unique properties, scientists hope to unlock secrets about the conditions present during the solar system's infancy. As exploration continues, each new discovery brings us closer to understanding the remarkable journey of this distant traveler now bound to Saturn's domain. High-resolution images of Phoebe's surface continue to inspire awe and deepen our appreciation for the diversity of worlds within our cosmic neighborhood. These visuals not only captivate viewers but also serve as vital resources for advancing our knowledge of the universe. Shifting our gaze from the enigmatic Phoebe, we now turn to another intriguing moon in Saturn's entourage, Dione. Recent findings hint at the possibility of cryovolcanic activity on this icy satellite, sparking excitement among scientists and raising new questions about its hidden depths. While Dione has long been considered a relatively quiet and unchanging world, fresh data suggests there may be more going on beneath its frozen surface than meets the eye. Cryovolcanism refers to the eruption of liquid water, ammonia, or methane instead of molten rock, as seen in traditional volcanoes here on Earth. Evidence pointing toward such activity on Dione comes from subtle but significant observations made by NASA's Cassini spacecraft during its flybys of the Moon. One key piece of evidence lies in the detection of faint traces of oxygen ions surrounding Dione. These ions could result from the interaction between charged particles in Saturn's magnetosphere and water molecules released into space through geysers or plumes erupting from the Moon's surface. In addition to these ion readings, researchers have also identified cracks and fractures across Dione's terrain that resemble features associated with tectonic activity. Such structural deformations might indicate internal heat sources capable of melting subsurface ice layers, creating reservoirs of liquid water under pressure. If true, this process could periodically force water vapor and other materials out through fissures onto the surface, much like what we see on Enceladus, one of Saturn's most famous active moons. The implications of cryovolcanic activity on Dione extend beyond just understanding its geological processes. They open up tantalizing possibilities regarding the existence of a subsurface ocean. A body of liquid water trapped beneath miles of ice would represent an environment where life as we know it could potentially exist. Although no direct proof exists yet for such an ocean on Dione, the presence of heat-generating mechanisms necessary for cryovolcanism strongly supports this hypothesis. Furthermore, if confirmed, Dione would join an elite group of celestial bodies including Europa, Ganymede, and Titan that harbor concealed seas capable of sustaining microbial organisms. Artistic renderings depicting possible geyser eruptions on Dione provide vivid illustrations of how these phenomena might look. Imagine towering columns of icy particles shooting high above the barren landscape, casting sparkling reflections in the dim sunlight filtering through Saturn's rings. While purely speculative at this stage, such visualizations help bring abstract scientific concepts to life, making them accessible to wider audiences while inspiring further investigation. As studies continue, each new discovery brings us closer to unraveling the mysteries surrounding Dione's potential cryovolcanic nature. By piecing together clues from remote sensing data, laboratory experiments simulating conditions within icy moons, and theoretical models predicting their behavior, scientists aim to construct a comprehensive picture of this fascinating world. What began as mere speculation now stands as a promising avenue for exploration, offering insights not only into Dione itself, but also into the broader dynamics shaping icy satellites throughout the solar system. Moving from the intriguing possibility of cryovolcanism on Dione, we now delve into another perplexing aspect of Saturn's character, its magnetic field anomalies. Unlike Earth's neatly aligned magnetic field, Saturn's magnetic environment presents a host of puzzling irregularities that continue to baffle scientists. These peculiarities not only challenge our understanding of planetary magnetism, but also hint at unique processes occurring deep within Saturn's interior. Saturn's magnetic field is surprisingly symmetrical compared to other planets in our solar system. Most planets exhibit some degree of tilt between their rotational axis and magnetic poles, creating complex interactions between their magnetic fields and surrounding space environments. However, Saturn defies this trend with its nearly perfect alignment. This unusual symmetry raises fundamental questions about how Saturn generates its magnetic field and whether conventional models can fully explain it. One significant anomaly lies in the strength and distribution of Saturn's magnetic field lines. Observations reveal subtle variations across different regions of the planet, suggesting the presence of localized phenomena influencing the overall structure. Researchers believe these fluctuations could stem from dynamic processes occurring within Saturn's core, where electrically conductive fluids interact under extreme pressure and temperature conditions. By studying these deviations, scientists hope to uncover clues about the composition and dynamics of Saturn's mysterious interior. Another intriguing feature involves the interaction between Saturn's magnetic field and its extensive ring system. Charged particles trapped within the magnetic field collide with dust and ice particles in the rings, producing faint glows visible in ultraviolet light. This phenomenon offers valuable insights into both the magnetic field's behavior and the physical properties of the rings themselves. Understanding these interactions helps refine models of Saturn's magnetic environment while shedding light on the intricate relationship between the planet and its iconic rings. Ongoing research employs sophisticated simulations and advanced observational techniques to unravel the mysteries of Saturn's magnetic field. Spacecraft like NASA's Cassini mission provided invaluable data during its exploration of the Saturnian system, revealing unexpected patterns and challenging existing theories. Scientists continue to analyze this wealth of information, combining it with laboratory experiments designed to replicate conditions found within Saturn's depths. Through these efforts, they strive to construct a comprehensive picture of how Saturn's magnetic field operates and evolves over time. Visualizing Saturn's magnetic field requires creative approaches to convey its complexity effectively. Graphics depicting magnetic field lines extending far beyond the planet's surface help illustrate the vast reach and intricate geometry of this invisible force. Animations showing charged particles spiraling along these lines provide dynamic representations of the magnetic field's influence on its surroundings. Such visual aids enhance comprehension by transforming abstract concepts into tangible imagery, making them accessible to audiences ranging from casual viewers to dedicated enthusiasts. As investigations progress, each new discovery adds another piece to the puzzle of Saturn's enigmatic magnetic field. By piecing together observations, theoretical models, and experimental results, researchers aim to unlock the secrets hidden within this fascinating planetary feature. What emerges will not only deepen our understanding of Saturn itself, but also contribute to broader knowledge about magnetic fields across the cosmos. Shifting our focus from the complexities of Saturn's magnetic field, we now journey to one of its fascinating moons, Tethys, where a colossal geological feature awaits exploration. Stretching across nearly the entire surface of this icy satellite is Ithaca Chasma, an enormous canyon system that stretches for thousands of miles and plunges several kilometers deep. This gargantuan fissure dominates Tethys' landscape, raising numerous questions about its origins and implications for the moon's internal structure. Scientists have proposed several theories to explain how such a massive canyon could form on a relatively small celestial body like Tethys. One prevailing hypothesis suggests that Ithaca Chasma resulted from the freezing and expansion of a subsurface ocean early in the Moon's history. As the liquid water beneath the icy crust solidified, it expanded, creating immense stresses that caused the surface to crack open. This process would have left behind the breathtaking chasm we observe today. Supporting this theory are observations indicating that Tethys might still harbor remnants of an ancient ocean, possibly trapped as a layer of liquid or slush beneath its frozen exterior. Another intriguing possibility ties the formation of Ithaca Chasma to tidal forces exerted by Saturn during Tethys' early evolution. These gravitational interactions could have stretched and compressed the Moon, generating enough stress to fracture its brittle outer shell. While less widely accepted than the subsurface ocean hypothesis, this explanation highlights the dynamic interplay between Saturn and its moons, shaping their surfaces over billions of years. Exploring the connection between Ithaca Chasma and Tethys' potential subsurface ocean reveals tantalizing clues about the Moon's internal composition and thermal history. If indeed an ocean once existed or continues to exist, it raises exciting prospects for astrobiology, suggesting conditions conducive to life may have been present at some point. The presence of salt and organic compounds detected on Tethys' surface further fuels speculation about the chemical richness of any hidden reservoirs below. Visual documentation of Ithaca Chasma provides stunning evidence of these monumental geological processes. High-resolution images captured by spacecraft missions reveal intricate details of the canyon's walls, showcasing jagged cliffs and layered deposits that hint at complex geologic activity throughout Tethys' past. These vivid portrayals bring the grandeur of Ithaca Chasma to life, offering viewers a glimpse into the extraordinary forces that sculpted this distant world. Studying Ithaca Chasma not only deepens our understanding of Tethys, but also contributes valuable insights into the broader context of icy moon dynamics across the solar system. By piecing together the story of this colossal canyon, researchers gain crucial knowledge about the interplay of tectonic forces, thermal evolution, and possible subsurface oceans, a narrative woven through the fabric of many moons orbiting gas giants. Each discovery adds another thread to the tapestry of planetary science, drawing us closer to unraveling the mysteries concealed within these enigmatic worlds. Turning our attention now to one of Saturn's most iconic features, let us delve into the intriguing phenomenon of its vanishing rings. These breathtaking structures, which have captivated observers for centuries, are not as permanent as they might seem. Recent studies suggest that the rings are slowly eroding, with various processes contributing to their gradual disappearance. Understanding these mechanisms provides a fascinating glimpse into the dynamic nature of Saturn's celestial adornment and raises important questions about how long we may continue to marvel at this planetary masterpiece. One primary factor in the erosion of Saturn's rings is the constant bombardment by micrometeoroids. These tiny particles, traveling through space at incredible speeds, collide with the icy ring material, gradually chipping away at its surface. Over time, this relentless assault causes the rings to lose mass, diminishing their brilliance and structure. Scientists estimate that this process alone could significantly reduce the ring's size over millions of years, altering Saturn's appearance in profound ways. Another critical mechanism involves gravitational interactions between the rings and Saturn's many moons. These interactions can lead to what scientists call ring-particle collisions, where smaller fragments within the rings collide and break apart. Such events contribute to the dispersal of ring material, accelerating the erosion process. Additionally, some material from the rings spirals inward toward Saturn due to gravitational forces, eventually falling into the planet's atmosphere. This phenomenon, often referred to as ring rain, further depletes the ring's mass and highlights the intricate balance governing their existence. Estimating the potential timeline for the ring's disappearance requires careful consideration of these factors. Current models suggest that the rings may survive anywhere from 10 million to 100 million years before fading into obscurity. While this may seem like an eternity compared to human timescales, it represents a fleeting moment in cosmic terms. The implications of such a transformation are staggering, as Saturn's distinctive silhouette would be forever altered, leaving behind a planet that looks quite different from the one we know today. Visualizing these changes adds another layer of intrigue to the story. Through advanced simulations, researchers can model the gradual evolution of Saturn's rings over millennia. These visual representations reveal how the rings might appear as they lose mass, becoming fainter and less defined. In some scenarios, certain portions of the rings could vanish entirely, while others persist in diminished form. Such simulations provide valuable insights into the complex interplay of forces shaping Saturn's rings and offer viewers a glimpse into the planet's possible future. The impact of these changes extends beyond aesthetics, touching on broader scientific questions about the origins and longevity of planetary rings. By studying the erosion processes affecting Saturn's rings, scientists gain vital clues about similar phenomena occurring elsewhere in the solar system. This research contributes to our understanding of the delicate equilibrium that sustains these remarkable structures and underscores the importance of preserving our observations while they remain visible. In contemplating the eventual fate of Saturn's rings, we are reminded of the transient beauty of the cosmos. What appears timeless and unchanging to us today is in reality subject to the ceaseless forces of nature. As we continue to explore and document these majestic formations, we deepen our appreciation for the intricate dance of matter and energy that defines our universe. And though the rings may one day fade from view, their legacy will endure, inspiring generations to come with tales of their awe-inspiring splendor. Shifting our focus now to one of Saturn's most enigmatic moons, let us explore the peculiar heat patterns observed on Mimas. Known for its striking resemblance to the Death Star from Star Wars due to its massive Herschel crater, Mimas has long fascinated scientists and space enthusiasts alike. However, recent thermal imaging data has revealed something truly unexpected. Mimas exhibits a heat distribution that defies conventional understanding. Initial expectations suggested that Mimas' surface would display relatively uniform cooling, given its small size and lack of significant geological activity. Yet, when NASA Cassini spacecraft captured detailed thermal maps of the Moon, it unveiled an astonishing pattern resembling a Pac-Man shape. This bizarre configuration, with warmer regions concentrated in specific areas rather than evenly distributed, has left researchers scratching their heads. The discovery raises fundamental questions about the internal dynamics of this seemingly inert celestial body. To understand these unusual heat signatures, scientists have proposed several theories involving potential internal heating mechanisms. One leading hypothesis suggests tidal flexing as a possible source of warmth beneath Mimas' icy crust. As Mimas orbits Saturn, gravitational forces exerted by the planet cause slight deformations in the Moon's shape. These stresses generate friction within the Moon's interior, producing heat through a process similar to how rubbing your hands together warms them up. While this mechanism might explain localized warm spots, it struggles to account for the overall asymmetry observed in the thermal data. Another intriguing possibility involves subsurface reservoirs of liquid water or slushy ice. If such hidden oceans exist, they could serve as conduits for transferring heat toward the surface, creating the observed temperature anomalies. Evidence supporting this theory comes from studies showing that even small moons like Mimas may harbor conditions favorable for maintaining liquid water under certain circumstances. Although direct proof remains elusive, the presence of a subsurface ocean would open exciting avenues for exploring the Moon's habitability potential. Further complicating matters is the role played by Mimas' unique orbital resonance with neighboring moons. This interaction influences both its rotation rate and orbital eccentricity, potentially affecting its internal structure and heat distribution. Researchers continue to investigate whether these factors contribute significantly to the puzzling thermal patterns seen on Mimas. By modeling various scenarios incorporating these elements, they hope to unravel the mysteries behind this fascinating phenomenon. Visual representations of Mima's heat map provide compelling insights into the Moon's thermal behavior. Using false color imaging techniques, scientists can highlight different temperature ranges across the surface, revealing intricate details otherwise invisible to the naked eye. These vibrant images depict stark contrasts between warm and cool zones, emphasizing the complexity of the processes at play. Such visualizations not only aid scientific analysis but also captivate audiences with their otherworldly beauty. The implications of Mima's surprising heat patterns extend far beyond the Moon itself, shedding light on broader planetary science questions. Understanding the mechanisms driving these thermal anomalies contributes to our knowledge of how small icy bodies maintain dynamic interiors despite their diminutive sizes. It challenges existing models of heat transport and energy dissipation in celestial objects, encouraging further exploration into the diverse range of physical processes shaping our solar system. As we delve deeper into the secrets of Mimas, each new discovery adds another piece to the puzzle of this remarkable moon. Its unexpected heat distributions remind us once again of the incredible diversity found throughout the cosmos and inspire continued curiosity about the unseen forces operating within some of its smallest inhabitants. Turning our attention now to another intriguing mystery surrounding Saturn's moons, let us explore the enigma of Rhea's possible ring system. Rhea, Saturn's second-largest moon, has long been studied for its icy surface and cratered landscape. However, in 2005, observations from NASA Cassini spacecraft hinted at something extraordinary, a faint system of rings orbiting this distant celestial body. If confirmed, Rhea would become the first known moon in our solar system to possess such a feature. The initial evidence emerged during a flyby when Cassini detected an unexpected asymmetry in the distribution of charged particles around Rhea. Scientists interpreted these findings as potential indicators of material being swept away by a ring system. The idea was tantalizing but not without challenges. Subsequent investigations using more precise instruments failed to provide definitive proof, leaving researchers puzzled about the nature of this phenomenon. Several factors contribute to the elusiveness of confirming Rhea's rings. First, the hypothesized ring system is incredibly faint, composed primarily of tiny dust particles rather than the reflective ice chunks found in Saturn's iconic rings. These minuscule components make detection extremely difficult even with advanced technology. Additionally, the gravitational forces exerted by Saturn itself may disrupt any attempts to maintain stable orbits for such delicate structures, further complicating their existence. Despite the lack of conclusive data, the possibility of rings around Rhea raises fascinating questions about the dynamics of moons in general. For instance, if Rhea does indeed harbor a ring system, it suggests that similar features might exist elsewhere in the solar system where current observational capabilities fall short. Moreover, understanding how such systems form and persist could offer valuable insights into the broader processes governing celestial mechanics. One plausible explanation for Rhea's rings involves collisions between small objects in its vicinity. Impacts on the Moon's surface or nearby debris clouds could produce fine particles that temporarily coalesce into a ring-like structure before dispersing over time. Another theory proposes that volcanic activity beneath Rhea's frozen exterior releases materials capable of forming rings, though no direct evidence supports this notion yet. Artistic interpretations of Rhea's hypothetical rings paint vivid pictures of what such a site might look like. Imagine delicate arcs of shimmering dust encircling the Moon, barely visible against the vast backdrop of space. These renderings serve not only as tools for visualizing scientific concepts, but also as reminders of the many wonders still awaiting discovery in our universe. Ultimately, the question of whether Re truly possesses rings remains open-ended, inviting continued exploration and investigation. What we do know is that this mystery adds another layer of complexity to our understanding of moons and their diverse characteristics. As technology advances and new missions venture deeper into the outer reaches of our solar system, perhaps one day we will uncover the truth behind Re's elusive rings, and along with it, unlock further secrets hidden among Saturn's celestial family. Shifting our focus now to the heart of Saturn itself, we delve into one of the most fundamental yet perplexing aspects of this gas giant, the nature of its core. Despite decades of study, the exact composition and structure of Saturn's core remain shrouded in mystery, leaving scientists with more questions than answers. What lies beneath the swirling clouds and immense atmospheric layers? How does it influence the planet's behavior and dynamics? Let us uncover the current theories and explore the implications of these models. At present, several competing hypotheses attempt to explain Saturn's core, each offering unique insights but none providing definitive proof. One widely discussed model suggests that Saturn possesses a dense rocky core surrounded by a layer of metallic hydrogen. This scenario aligns with observations of other gas giants like Jupiter, where similar conditions are believed to exist. In this configuration, the core would consist primarily of silicates and metals, compressed under extreme pressure and temperature to form a solid mass at the planet's center. Such a structure could account for some of Saturn's gravitational anomalies and magnetic field characteristics. However, recent research has introduced alternative possibilities that challenge traditional assumptions. Another prominent theory proposes that instead of a well-defined core, Saturn may harbor a fuzzy or diffuse interior. In this model, heavy elements are not concentrated in a single central region but distributed throughout the planet's inner layers. This distribution creates a gradual transition between different materials, making it difficult to pinpoint an exact boundary for the core. Proponents argue that such a setup better explains certain observed phenomena, including the planet's rotation rate and density distribution. Yet another intriguing idea involves a hybrid approach, combining elements from both previous models. According to this hypothesis, Saturn might have a small, dense core surrounded by a broader zone of mixed heavy elements. This layered arrangement could resolve inconsistencies seen in earlier interpretations while accommodating newer data gathered by missions like Cassini. By integrating multiple perspectives, researchers hope to construct a more comprehensive understanding of Saturn's internal architecture. Each of these models carries significant implications for our knowledge of planetary formation and evolution. For instance, if Saturn indeed features a well-defined core, it supports the core accretion theory of planet formation, wherein gas giants grow around a solid seed. Conversely, evidence favoring a diffuse interior challenges this paradigm, suggesting alternative mechanisms such as gravitational instability. Understanding Saturn's core is thus crucial not only for explaining its own properties but also for refining theories about how planets form across the universe. Visual representations play a vital role in illustrating these complex ideas. Cutaway diagrams depicting possible core configurations help bring abstract concepts to life, allowing viewers to grasp intricate details more easily. These graphics often show variations in density, temperature, and composition within Saturn's interior, highlighting key differences among competing models. Whether showcasing a compact core, a fuzzy distribution, or a layered hybrid, such visuals serve as powerful tools for enhancing comprehension and sparking curiosity. As investigations continue, new technologies and analytical methods promise to shed further light on Saturn's enigmatic core. Upcoming missions equipped with advanced sensors and imaging capabilities may provide critical data needed to distinguish between existing theories or reveal entirely novel insight. Until then, the question of what truly resides at Saturn's center remains open-ended, inviting speculation and inspiring exploration. What we do know is that unraveling this mystery holds profound significance for expanding our understanding of not just Saturn but the entire cosmos. Moving our attention now to one of the most fascinating orbital dances in the solar system, let us explore the intricate relationship between Saturn's moons Epimetheus and Janus. These two small satellites perform a cosmic ballet that has intrigued astronomers for decades, offering a glimpse into the complex gravitational dynamics at play within Saturn's system. Epimetheus and Janus share an unusual arrangement, orbiting Saturn at nearly the same distance. Their paths are so close that they periodically exchange places, swapping orbits in a rhythmic cycle that lasts about 4 years. This phenomenon arises due to their mutual gravitational pull, which creates a delicate balance where neither moon can settle into a stable orbit without affecting the other. As they approach each other during their closest encounters, their gravitational forces act like invisible hands, gently nudging them into new trajectories. To understand this process better, imagine two dancers moving around a central point, occasionally exchanging positions while maintaining harmony. When Epimetheus and Janus come near one another, the outer moon slows down slightly due to gravitational interaction, causing it to fall inward toward Saturn. Simultaneously, the inner moon speeds up, propelling it farther away from the planet. Over time, this dynamic causes their roles to reverse, with the previously inner moon becoming the outer moon and vice versa. What makes this orbital dance particularly intriguing is its precision and regularity. Despite the chaos that might seem inherent in such a system, Epimetheus and Janus maintain a predictable pattern, suggesting a deeper order underlying their movements. Scientists believe this stability stems from the moon's relatively similar masses and their location within Saturn's gravitational influence. However, many questions remain unanswered. For instance, why did these moons form so close together? Was their proximity a result of chance or part of a larger evolutionary process? The puzzle deepens when considering how long this orbital dance has been occurring and whether it will continue indefinitely. Some theories propose that over millions of years, tidal forces exerted by Saturn may gradually alter the orbits of Epimetheus and Janus, potentially disrupting their current rhythm. Others speculate that collisions or interactions with debris in Saturn's rings could introduce unforeseen changes to their paths. Visualizing this celestial choreography provides a powerful tool for understanding its mechanics. Animations showing the orbital exchange process reveal the elegance of the system, illustrating how the moons gracefully swap positions without colliding. These visuals highlight the interplay of forces driving their motion and help clarify concepts that might otherwise seem abstract. By observing the gradual shifts in their orbits, viewers gain insight into the broader principles governing planetary systems. This unique phenomenon also raises broader implications for our understanding of orbital mechanics and satellite behavior. The case of Epimetheus and Janus demonstrates that even seemingly simple arrangements can harbor unexpected complexity, challenging conventional assumptions about space dynamics. Studying their interaction offers valuable lessons for modeling other multi-body systems, both within our solar system and beyond. As research progresses, advanced simulations and observational data continue to refine our comprehension of this extraordinary orbital dance. Future missions equipped with enhanced instruments may capture more detailed information about the moon's movements, shedding light on the mechanisms driving their periodic swaps. Until then, the cosmic waltz of Epimetheus and Janus remains a captivating reminder of the mysteries still waiting to be uncovered in Saturn's vast domain. Shifting our focus now to another captivating phenomenon within Saturn's system, let us delve into the intriguing relationship between Prometheus and Saturn's F-ring. This small moon, named after the mythological figure who stole fire from the gods, plays a pivotal role in shaping one of Saturn's most dynamic and enigmatic features. Prometheus orbits just inside the F-ring, a narrow, wispy structure that extends far beyond Saturn's main ring system. Despite its diminutive size, Prometheus exerts significant influence over the F-ring through gravitational interactions. As it moves along its orbit, Prometheus periodically ventures close enough to the ring to pull material inward, creating dramatic effects that astronomers have likened to braids and knots. These structures form as particles in the ring are stretched, twisted, and reorganized by the moon's gravitational tug. To better understand this process, imagine a person weaving threads on a loom, pulling them in different directions to create intricate patterns. Similarly, Prometheus acts like an invisible weaver, sculpting the F-ring into complex shapes during its closest approaches. The result is a constantly evolving ring structure, where braids and knots appear and disappear over time, offering a mesmerizing display of celestial mechanics. What makes these interactions particularly fascinating is their unpredictability. While scientists have developed models to explain the general behavior of Prometheus and its effects on the F-ring, many questions remain unanswered. For instance, why do certain features persist longer than others? How does the composition of the ring material affect its response to Prometheus' gravitational pull? And what role do other nearby moons, such as Pandora, play in maintaining the F-ring's overall stability? Time-lapse sequences captured by spacecraft like Cassini provide valuable insights into these processes, revealing the dynamic nature of the F-ring in stunning detail. These animations show how Prometheus' gravitational influence creates ripples, gaps, and streams of material within the ring, highlighting the delicate balance between forces at work. Observers can witness the formation and dissipation of braids and knots in real time, gaining a deeper appreciation for the complexity of Saturn's ring system. The study of Prometheus' interaction with the F-ring also holds broader implications for understanding similar phenomena elsewhere in the universe. It demonstrates how small bodies can significantly impact their surroundings, even when they appear insignificant compared to larger celestial objects. This knowledge contributes to our understanding of planetary rings, asteroid belts, and other systems governed by gravitational dynamics. As research continues, scientists hope to uncover more secrets about this remarkable relationship. Advanced simulations and new observational data promise to refine existing models, shedding light on the mechanisms driving these interactions. In the meantime, the interplay between Prometheus and Saturn's F-ring stands as a testament to the wonders of our solar system, inviting us to marvel at the intricate choreography of space. Moving our attention now to another perplexing aspect of Saturn's behavior, let us examine the mysterious variability in its day length. Unlike Earth, where the rotation period remains consistent over long periods, Saturn presents scientists with a puzzling phenomenon. Its apparent day length seems to fluctuate depending on how it is measured. This inconsistency has baffled researchers for decades and continues to spark debates within the scientific community. Saturn's day length is traditionally determined by studying its radio emissions, which are believed to originate from processes deep within its atmosphere. These emissions act as natural signals that astronomers use to track the planet's rotation. However, measurements taken at different times have revealed discrepancies, suggesting that Saturn's day might not be as constant as once thought. For instance, data collected by the Voyager spacecraft during the early 1980s showed a rotation period of 10 hours, 39 minutes, and 24 seconds. Yet subsequent observations made by the Cassini mission more than 2 decades later indicated a slightly longer period of 10 hours, 45 minutes, and 45 seconds. At first glance, this difference may seem minor, but it raises fundamental questions about our understanding of Saturn's internal dynamics. If the planet's core is rotating steadily, why do these variations occur? Scientists have proposed several theories to explain this phenomenon. One possibility involves interactions between Saturn's magnetic field and its upper atmosphere. Changes in atmospheric winds could potentially alter the observed radio emission patterns, creating the illusion of a changing rotation rate. Another hypothesis suggests that the planet's magnetosphere, influenced by external factors such as solar wind pressure, might distort the measurements further. Despite these explanations, many challenges remain in accurately determining Saturn's true rotation period. The gas giant lacks a solid surface or easily identifiable landmarks that would allow direct tracking of its spin. Instead, researchers must rely on indirect methods like radio emissions, which introduce additional layers of complexity. Complicating matters further, Saturn's magnetic field axis aligns almost perfectly with its rotational axis, making it difficult to distinguish between the two. On other planets, mismatches between these axes provide valuable clues about rotation rates, but Saturn offers no such advantage. To better understand this variability, scientists have turned to advanced modeling techniques and comparative studies of other gas giants. By analyzing historical data alongside new observations, they hope to uncover trends or cycles in Saturn's measured rotation periods. Graphs depicting these changes over time reveal subtle shifts, hinting at underlying processes yet to be fully understood. Some researchers speculate that seasonal variations or long-term oscillations in Saturn's interior might contribute to these fluctuations, although concrete evidence remains elusive. As investigations continue, one thing becomes clear. Saturn's day-length variability serves as a reminder of how much we still have to learn about this enigmatic planet. Each new discovery adds another piece to the puzzle, bringing us closer to unraveling its secrets while simultaneously raising fresh questions. The interplay between theoretical models and real-world observations keeps driving scientific progress forward, fueling excitement among astronomers worldwide. With future missions planned to explore Saturn and its surroundings, there is hope that answers to some of these mysteries will soon come to light. Shifting our focus now to one of the most tantalizing questions in planetary science, let us explore the potential for life within Saturn's vast and complex system. As we've delved into the mysteries surrounding this gas giant and its moons, a recurring theme has emerged: the possibility that conditions suitable for life might exist in some corners of the Saturnian realm. From Enceladus Subsurface Ocean to Titan's methane-rich environment, each discovery brings us closer to understanding whether these distant worlds could harbor living organisms. To begin with, consider Enceladus, the small but remarkable moon famous for its geysers spewing water vapor and ice particles into space. These plumes originate from a global ocean beneath the icy crust, offering scientists an unprecedented opportunity to study extraterrestrial liquid water without needing to drill through kilometers of ice. Analysis of samples collected by the Cassini spacecraft revealed not only water but also organic compounds, salts, and potentially even hydrothermal vents on the seafloor. On Earth, such environments are known hotspots for microbial life, raising hopes that similar processes might occur on Enceladus. While direct evidence of life remains elusive, the presence of all the key ingredients, water, energy sources, and organic molecules, makes this moon one of the top candidates for habitability in our solar system. Moving outward, we encounter Titan, Saturn's largest moon and a world unlike any other. With a thick atmosphere rich in nitrogen and methane, Titan boasts surface features eerily reminiscent of Earth, including lakes, rivers, and rain. But instead of water, these bodies consist of liquid hydrocarbons. Although temperatures plummet far below freezing, making traditional life as we know it unlikely, researchers speculate about alternative biochemistries that might thrive under such extreme conditions. For instance, hypothetical methanogenic organisms could metabolize hydrogen and acetylene dissolved in the methane seas. producing energy through chemical reactions rather than sunlight-dependent photosynthesis. While speculative, this theory highlights the importance of broadening our definition of habitability when exploring alien environments. Beyond these two leading contenders, other moons in Saturn's family present intriguing possibilities as well. Dione, for example, shows signs of cryovolcanic activity, suggesting it too might possess a hidden ocean. Similarly, raises questions about its own potential internal reservoirs, though less is currently known about this moon's composition. Even tiny Hyperion, with its chaotic rotation and sponge-like appearance, adds another layer of complexity to the search for life, reminding us how little we truly understand about these distant worlds. Synthesizing insights gained from previous sections, several patterns emerge regarding what makes a celestial body potentially habitable. First, the availability of liquid water or analogous solvents like methane appears crucial for fostering prebiotic chemistry. Second, access to stable energy sources, whether from tidal heating, radioactive decay, or sunlight, plays a vital role in maintaining the necessary conditions for life over geological timescales. Third, the presence of organic compounds serves as building blocks for complex molecules essential for biological processes. By combining these factors, scientists can narrow down which moons warrant further investigation while prioritizing missions that target high-priority targets. Visualizing the Saturnian system as a whole reveals just how diverse and dynamic it truly is. A composite image showing all the major moons together paints a vivid picture of their unique characteristics, from Enceladus' brilliant white surface streaked with tiger stripes to Titan's hazy orange glow masking its mysterious terrain. Each moon tells its own story, contributing pieces to the larger puzzle of life's potential beyond Earth. In conclusion, the search for life around Saturn represents more than just scientific curiosity. It embodies humanity's enduring quest to discover if we are alone in the universe. Every mystery uncovered brings us one step closer to answering this profound question, inspiring future generations of explorers to venture deeper into the cosmos. And so, as we continue unraveling Saturn's secrets, remember that the answers we seek may lie not only among the stars but also within the shadowy depths of its enigmatic moons. To wrap up our journey through the 25 unexplained mysteries of Saturn, let's take a moment to reflect on just how extraordinary this gas giant and its family of moons truly are. From the mesmerizing hexagon at Saturn's north pole to the intricate dynamics of its rings, each discovery has revealed layers of complexity that continue to challenge our understanding of the universe. Despite decades of exploration and countless observations from missions like Voyager and Cassini, so much about Saturn remains shrouded in mystery. Throughout this video, we've uncovered some of the most fascinating enigmas surrounding Saturn. We marveled at the strange radio emissions that vary between hemispheres, pondered the chaotic rotation of Hyperion, and explored the potential for life beneath the icy crusts of Enceladus and Titan. Each mystery adds another piece to the puzzle, yet it becomes increasingly clear that the full picture is far from complete. The more we learn, the more questions arise, driving us to push the boundaries of science and technology even further. What stands out is not only what we've discovered, but also what we have yet to uncover. For every answer, there are 10 new questions waiting to be asked. How long will Saturn's rings last? What lies hidden within the planet's core? Could one of its moons harbor life as we know it, or something entirely different? These mysteries remind us of just how vast and uncharted the cosmos still is. As we conclude, I invite you to think about your favorite mystery from today's exploration. Was it the haunting beauty of Saturn's auroras, or perhaps the intriguing possibility of hydrothermal vents on Enceladus? Share your thoughts in the comments below. I'd love to hear which mysteries resonated with you the most. Your curiosity fuels the next chapter of discovery, and if you enjoyed diving into the depths of Saturn's secrets, don't forget to hit that subscribe button for more adventures across the stars. There's always more to explore, and together we can keep unraveling the wonders of space. Thank you for joining me on this cosmic journey. Until next time, keep looking up.